This video is about differential equations. A differential equation is just an equation that has a derivative in it, and the derivative can be of any order. So we can have like a first derivative equals 2x. We can have an actual like other things in the equation, so x plus the second derivative of y is equal to 7, or we can have something like y prime is equal to y. All of those are differential equations because they all have derivatives. We're going to focus on first order differential equations, which is just a differential equation whose highest derivative is a first derivative. So up here, this is a first order differential equation, and this is a first order. This would be a second order because the highest derivative is a second derivative. We're also going to focus on a type of differential equation called a separable first order differential equation. So when you have those, these are the 4 steps that we need to go through. First, we separate the variables, which will make more sense on the next slide, but we're just going to try to get x and y apart from each other. So we've got only x on one side of the equal sign and only y on the other side of the equal sign. Then once we separate the variables, we integrate each side, and then steps 3 and 4 are kind of interchangeable. It sort of depends on the problem and the initial condition and everything that they give you. So sometimes it's better to solve for y first, sometimes it's better to find c, but if you don't have to find c, then obviously we're going to just solve for y and stop there. Here's an example of a differential equation. So it says solve dy dx equals x over y, and if you notice, this might look sort of similar to implicit differentiation, because what we're doing when we solve differential equations, we're undoing an implicit differentiation problem. Alright, so we start with step 1, separating the variables. So I'm cross multiplying. I get the y's on one side and I get the x's on the other. dy counts as a y and dx counts as an x. So I don't want to have a mixture of x's and y's. I need to separate them to 2 different sides. After I separate my variables, then I integrate. So I just take y dy and then I put a little integral sign in front of it. And same thing, x dx, and put a little integral in front of it. Then I'll take the integral. So remember, when you're integrating y dy, dy is our variable. So we just integrate this like normal. It's 1/2 y squared. And then over here, x is our variable, so it's going to be 1/2 x squared. With the plus c, really, you have a plus a constant on both sides, but it doesn't make any sense to separate those out, so we just combine both of our constants and put it on one side. Traditionally, we put it on the side that has the x with it, just because I know that eventually I'm going to solve this for y, so I might as well start with the c on the proper side. And then I just do some algebra to solve this, so multiply by 2, and then take the square root, which gives me a plus or minus square root of x squared plus c. So this is my solution. Another acceptable solution for this one would be x squared minus y squared equals c. Here's a really basic example. You can use separation of variables for a lot of integrals that we've done in class, but it doesn't always make sense to do that. So, like, yes, I can get the y's on one side and the x's on the other side and then take the integral, but I end up with y equals 2x plus c. Or, if I look at it from the very beginning, if I integrate that, I know I end up with y, because the derivative of y with respect to x is dy dx, and then the derivative of 2x is 2. So I don't always need to do separation of variables, but if you want to, it might work. Here's one more example. I included this one mainly to show you how to solve for y, because this is a common thing that you'll see in AP problems. So we have dy dx equals y over x, and we have to separate the variables again, which means the y we need to move down here, and then the dx we're going to move up here. So we end up with dy over y and dx over x. And then we take the integral of both sides. On the left, I know dy over y or dx over x is a really common integral, so anytime you see that, you should just know that's natural log of whatever the variable is. So on the left I have natural log of y, on the right I have natural log of x, and then I'll put my plus c over here. Now, this is okay, but it's not a great solution, so I really need to get y by itself. And to get rid of that natural log, I can use e. So I'll do e to the natural log of y, and then because I made the base of the left side e, I also have to do that on the right side. So I have e, and then to the entire side, natural log of x plus c. Now, e and natural log are inverse operations, so they cancel out, and the y just falls down, basically. Same thing over here. There's a couple of different things going on though. So I have two things added together in the exponent, which means I can split them up into two things that have the same base that are multiplied together. So I have e to the natural log of x for the first part, and then the plus sign tells me I also have e to the c, and those are multiplied together. E to the natural log of x, those cancel out the same way they did up here for the y's, so this is just x. And then e to the c, so I have e raised to a constant, which is the same thing as a constant, because if I square e, or if I raise e to the 1.5 or whatever, it's just going to give me a constant. So e to the c changes into just c. It's some constant, I don't care which one it is right now. And then you could write y equals x times c, but it just looks a little bit weird, so y equals c times x is a better solution for this. Alright, so go ahead and try this one. We have dy dx equals 6y squared x. You don't have to figure out what c is, but you do have to solve the equation to get y by itself. So go ahead and pause the video here, and when you're ready, restart the video, and we'll look at the solution together. Alright, so here we can see we separate the variables. You can really put the 6 either spot. You can put it with the y squared down here, or you can leave it with the x. Usually it's just a little bit easier to leave it with the x, so that's what I tend to do. Alright, so we have dy over y squared, and then 6x dx. On the left side, we rewrite it with negative exponents just to make it easier to take the integral. On the right side, that's the integral. It just is what it is. So the integral of y to the negative 2 is negative y to the negative 1, and the integral of 6x is 3x squared. And then plus c needs to go somewhere, so we put it over here. Alright, so I did two things from here to here. First, make everything negative. So really that just means that the x is going to be negative because this c sort of absorbs everything that gets done to it. As long as it's still a constant, that's all I care about. Alright, so I have 1 over y equals negative 3x squared plus c. And I don't want 1 over y, I just want to know what y equals. So I have to take the reciprocal of this side, which is just y, and then I also take the reciprocal of the right side, which gives me 1 over the quantity of negative 3x squared plus c. And that is the solution we would expect for this problem. Here's an example where we have to figure out what c is. So they'll say something like satisfy the given initial condition, or they will just give you an initial condition. So we have to find a particular solution. Dy dx is equal to the square root of xy, so remember we can split that into two separate square roots, which makes it easier to move y on one side and leave x on the other. Then we take our integrals, so the integral of y to the negative 1/2 is 2 times y to the 1/2, and then the integral of x to the 1/2 gives me 2/3 x to the 3/2. And I'm going to go ahead and put my plus c on the side with the x, just because. I could put it with the y, but then I'd have to move it over here anyways. Because the next step is solving for y, so I divide everything by 2. And remember, we're dividing the constant by 2, but it's still a constant, so I don't have to write divided by 2 with it. And then, at this point, I could solve it for y, but it's actually a little bit easier since I would have to square it and then square root it, so it's not worth the hassle. So instead of solving it for y from here, I'm going to take my initial condition and plug it in. So y is equal to 2 when x is equal to 1, so I plug those in, and then I just rearrange it to figure out what c is. So c is root 2 minus 1/3, and then I take this and plug it back into my equation up here. So we have y to the 1/2 equals 1/3 x to the 3/2 plus our constant, which is root 2 minus 1/3. And then the very last step, I'm going to solve it for y. So I had y to the 1/2, which is the square root of y, so I just square both sides. And when you square both sides, make sure you're squaring the entire side. And this looks a little bit weird, but just to clarify, that's a 3 right there. Here's one for you to try. It's a little bit more complicated because it's got a natural log, so you might have to use u substitution to solve it. And our initial condition is y of 1 equals 2. So go ahead and pause the video, and when you're ready, restart it, and we'll look at the solution. Alright, so first we have to get the y on the other side, so y moves over here, and then dx moves over there, and this is what we get. Taking the integral of y dy, I get 1/2 y squared, And then the integral of natural log of x over x gives me 1/2 times the quantity of natural log of x squared plus c. If you need to see how to get from this step to this step, you can look at the purple writing over here. Feel free to pause the video to do that if you need. And then the next thing I do, I'm going to solve for y, so I'll multiply by 2 on both sides, which gives me y squared equals the quantity of natural log of x squared plus c. And then from here, instead of taking the square root and then having to do weird stuff, I'm going to just plug in my initial condition. So y was 2 and x was 1. And then the nice thing is natural log of 1 is just 0. So really I have 2 squared equals c, or 4 equals c. And now I can put that back into this equation. And I get y squared equals natural log of x squared plus 4. And then I can take the square root of this, so we go my final solution, y equals plus or minus the square root of natural log of x, quantity squared, plus 4. And now I know it has a plus or a minus, but if I look at my initial condition, when I plugged in 1, I should get a positive answer out, which means I really don't need this negative here. Y just equals the positive square root. And that is the end. As always, ask if you have questions.